Welcome to week 5. Today I want to focus on dose response. So for the past 2 weeks, we've really been looking at estimating exposure to pathogens, specifically SARS-CoV-2. Today I want to take that and look at how we model the estimation of health effects using a dose response model. So I'll start by looking at what the data itself looks like. Some of the data comes from animals, and so I'll talk about what other information we can obtain from animal studies. I'll talk about the models themselves that we use, why we need to use them, and how they were developed. I'll give you an overview of how we fit the models, although I'm not going to go into a lot of the nitty-gritty computational software for doing it, but present the results. And then end up by talking about how we describe not just the likelihood of getting ill, but when an adverse event might occur, predicting the time course. So I'll start by talking about what data looks like. And basically, dose response data is obtained from what's called an experimental study. We take a study population, whether it's groups of animals or groups of human volunteers. We randomize them to control for any other factors that could very well influence the response. We divide them into groups and we administer different doses to each one of those randomized groups. Now, there are various ways of doing this. Often these studies are conducted using what's called blinding. A single blind study is where the investigator, where the subject rather, doesn't know the dose, and obviously that's relevant for human studies. Animals presumably have no knowledge. And a double-blind study is where neither the subjects nor the investigators know the dose until after the results are in. It adds reliability, but it complicates the conduct of the study. And a double-blind randomized study, as we see from the present literature, is often considered the gold standard in the context of pharmaceutical testing or vaccine testing. You've seen the acronym RCT in the popular press for randomized controlled trial. I'll give you an example of one of these studies in the context of estimating infectivity of a pathogen that's very important in drinking water. About 25 years ago, when Cryptosporidium parvum, which is a protozoan, emerged as a significant waterborne pathogen, a group of researchers at the University of Texas Health Science Center at Houston did a study in which human volunteers, primarily students, were administered known amounts of oocysts, a known dose. Bolus means a single event, and their response examined in terms of gastrointestinal symptoms, illness, and so forth. Cryptosporidium parvum in healthy individuals is mild to moderate, and so there was no concern about severe consequences from the effect, but the health of the volunteers was well monitored, and their health prior to being enrolled in the study was carefully checked to be sure that they were in fact healthy. This paper was published in New England Journal of Medicine. And the results of this study are depicted in summary fashion in this graph. So various doses from about 10 oocysts all the way up to 1 million were administered. And at each dose group, some number of subjects were administered that dose. The red circles represent the subject at that dose who were positive. So at the low dose, 5 were positive, 4 were negative, and the proportion positive given on the left-hand axis. Actually, excuse me, the red circles are not positive. The red circles are total number of subjects. So we'll talk about how to fit this later. The blue curve is simply fitting the proportion positive at each dose as a function of dose. So it appears to be an increasing trend. And obviously at high dose, essentially everybody is affected. An animal study is done much the same way, except using animals rather than humans. The advantage of an animal study is there's more flexibility in how we control other exposures. So in that cryptosporidium study I just told you about, once the subjects were administered the dose, they were allowed to proceed with their normal activities, but they were periodically monitored, asked to take their temperature, record their health status, and so forth. With animals, you can keep them controlled. You know their diet, you know their other conditions. With the human study, with the volunteers, each of the subjects may have had other exposures that caused adverse effect, which is one of the reasons why, particularly in a human study, you want to randomize the subjects administered a dose. And then finally, in animal studies, there's a potential for mechanistic examination, how the disease works, how other exposures or stress, or how markers of susceptibility or age or immune status might affect response to a pathogen. The downside of animal studies is that typically the animals used are a very closely controlled, often inbred, homogeneous population. So you don't have the impact of human variability that you might have in the case of a human study. Now, an experimental study can tell us this is where we get most of our dose response data from, whether it's human or animal. The animal studies have the potential to give us mechanistic information, and particularly the impact of multiple and dynamic exposures. That cryptosporidium exposure study I told you about, one single bolus dose administered at one time. With animal studies, we might have a program of multiple doses, or maybe even expose groups of animals to multiple pathogens or to a pathogen and a chemical stressor. We can modify the standard dose response study to look at time dependency, incubation time. How does time influence body burden? Are there physiological markers that we can use to determine what the effect or the exposure might have been? We can also do, especially with animal studies, investigations in secondary transmission. I'll talk about that momentarily. And we can look at modifications in susceptibility. So this was a study that was reported 7 years or so ago, and by a group that was concerned with influenza H7N9. There was thought that H7N9 could be a potential pandemic strain. And they were able to use an animal model of ferrets. And I'll come back to ferrets as well, because that's being used as a model in SARS-CoV-2. So they exposed ferrets to influenza. And then they did one of two things. They had a second group of ferrets that were isolated from the first group. And they took the nasal secretions from the first group of ferrets who were infected and exposed the second group of ferrets to those. And then with another group of ferrets, they were kept completely isolated except for an air connection between the cage of the first group and the second group. And that was to test whether or not aerosols could be generated from the infected ferrets that would result in an adverse outcome in the second group. And so here's a figure with their data. This top left-hand graph shows two particular strains of the virus. The load in nasal secretions in TCID50. So they actually cultured the virus as a function of days since inoculation. So in the case of influenza, roughly after about 1 day or so, you start to get substantial viral shedding from both of those strains. These bottom two left-hand figures represent multiple groups of animals that were inoculated with the application of the nasal secretions from the first group. And basically you see that there's roughly the same incubation curve for those two strains as there were in the animals that were primarily exposed. So that illustrates that direct contact can be a route of exposure, which is not surprising. But what is surprising, and this is a control group down here, is that these groups of ferrets were administered only the ER coming from the first set of cages. And you see roughly after day 2, which is really day 1 plus 1 day, there's substantial occurrence of viruses measured by TCID in those second group of animals that were exposed to the aerosol. So this really is a strong indicator for this influenza virus of secondary contact by aerosols. Now, I mentioned that ferret study because that was a published study. Here's a study that was recently put up on bioRxiv, April 17, 2020. And from our first discussion question, you know the issues with preprints. So this has not yet been peer reviewed, and there are issues associated with that. But this is one of the strongest research groups within Europe at Erasmus University in the Netherlands. So we have a high sense of reliability and validity for this study. And in fact, one of the authors, Marion Koopmans, was on the WHO Special Advisory Committee that advised the director to declare SARS-CoV-2 a pandemic. So the design of the study was very much the same as the influenza study, again with ferrets. The left-hand figure represents the ferrets that were primarily exposed. The right-hand figure represents ferrets that were exposed by air and by direct contact. And I've copied the conclusions. The pattern of virus shedding in direct contact and indirect recipient ferrets, meaning those that inhaled the aerosols, were similar to those of inoculated ferrets, showing that the ferrets could be infected by either direct contact or by aerosol. And so the authors say that this very much supports the implementation of community-level social distancing in the context of the SARS-CoV-2 pandemic. Now, experimental studies have pros and cons, as do all experiments. For animals, I mentioned the idea that these studies are often done with genetically homogeneous inbred animals. They may not be representative of biological heterogeneity, and we need to ask how to validate that with human data. With human studies, we can't use the most susceptible individuals because ethical considerations exist, and obviously we can't experiment with agents where lethality is a substantial likelihood of consequence. For both animal and human studies, you need special experimental expertise. For animal studies, you need containment laboratories and special handling. For humans, you obviously need a well-trained medical and clinical staff. But these experimental studies have good ability to generate data that we need for dose response. So let me describe how we model these data and why we need a dose response model in the first place. So typically we want to be sure that the risk from exposure remains low. And I'll talk about the issue of what risk is acceptable at the end of the class today. But let's say it's 1 in 1,000 or 1 in 10,000. We can really never do a direct study, even with animals, to assess the dose that would correspond to such a low risk. To do a study to directly determine the 1 in 10,000 exposure level, we would essentially need some multiple of 10,000 animals. And that's simply even with an animal study, a multi-million-dollar study. And so therefore we do data, we do experiments at larger exposures, greater exposures, with a greater proportion of individual positives in order to extrapolate or interpolate to low doses. And I put both the words extrapolate and interpolate there because in one sense, we're interpolating between 0 and a low dose. In another sense, we're extrapolating below the lowest dose that we might use in our experiments. So let me talk about what I mean by dose. So what I'm talking about here in the context of dose response is a population average, the average administered to a population. And so that could be any positive number, including with a fractional portion. Let's say I release 10 organisms into a room where 100 people are exposed. And I'll assume for the moment that all those 10 organisms will be inhaled by the people in the room. So the average dose in that case would be 10 over 100, 0.1. There's no difficulty with a fractional dose. We can also talk about dose as the actual number that an individual experiences. So this can be fractional, but obviously with organisms, those have to be integer. So in my hypothetical example, some individuals, most of the individuals in that case, with an average dose of 0.1, will be exposed to no organisms. Some will be exposed to 1, and probably a small fraction might be exposed to 2 because of randomness. And I'll talk about how to describe that quantitatively. The third type of dose we can talk about is the retained dose, the retention, which is particularly an issue for inhaled organisms. So not everything you inhale is retained within your lungs. Some is exhaled. And so we might want to correct the dose for the fraction that's retained, which will be a function of particle size, of the subject, and so forth. And then finally, we can talk about what the body burden is after multiplication. So when an organism is inhaled and retained, some of the organisms will multiply in vivo in the body. And it's really only then that we start to get the pathogenic effect. So let's say even one organism is inhaled. Some fraction of people who inhale and retain one organism will have a situation where the one organism completely dies with no adverse consequence. But some other fraction of the people will have an experience where the one organism multiplies to hundreds, thousands, maybe even millions or more. And it's really when you get the multiplication that you get an adverse effect that leads to infection, illness, and in severe cases, obviously death. So what do we use for a dose response model? Well, the model should consider the fact that the organisms themselves are discrete. They're particles. And so if we have a small number of organisms, there's random variability, especially at low dose. Imagine yourself sitting in the Great Court when we were open and counting the number of students that descend the stairs into the lobby in 1 minute. Now, during the breaks between class, traffic is less. Maybe on average, we'll have half a student descending per minute. But in any 1 minute, we might have 1 student, we might have 2, we might have 4, we might have 10 if they come with a group. So there's variability, there's randomness to that. And we need to describe that variability. The other aspect of dose response is that if a single organism is inhaled, if it remains within the lungs, it may or may not survive. There's a certain probability of surviving versus not. And if it survives, it may colonize and multiply to high concentrations. And this concept is called the birth-death process, now of the microorganism, of the pathogen within the host. So the simplest model that we can derive, and I in fact derived this back in the early 80s, is if we have the random distribution of particles being described by a Poisson distribution among different doses. A single organism is capable of producing an infection if it arrives at an appropriate site. You don't need two to coincidentally arrive. And then each organism has an independent, identical probability of surviving to reach and infect at that site. And that individual survival probability is described by the parameter K. So the exponential distribution is the probability of adverse effect. Or you can look at this as the proportion of individuals who get that average dose who will experience the adverse effect as a function of the average dose given that dose response parameter K, which is the probability of surviving. If K equals 1, that tells us that once an organism lands at an appropriate site, with certainty, it will multiply and infect and go on to cause infection and then ultimately illness. If K is less than 1, it tells us that only a fraction will survive. So the exponential has a single parameter associated with it. And I'll show you graphs of the exponential versus the next model, the beta Poisson, in a minute. The beta Poisson starts with the exponential, but rather than K being a constant, K itself has variability, which are given by the beta probability distribution. The beta distribution is a distribution describing the proportion of an occurrence between 0 and 1. And the main difference between the beta Poisson and exponential, and I'll show you the equation for beta Poisson, is that beta Poisson has two parameters. Versus the exponential having a single parameter K. And also that the curves are more shallow than the exponential. So here are graphs of the exponential and beta Poisson. The original form in which the beta Poisson was written was this form. It can be recast by defining additional defining new parameters in this way. Particularly people from the biological sciences find this more satisfying because one of the parameters winds up being the number of organisms, the dose, that gives 50% infectivity. I should also say that this is really an approximate form to the beta Poisson. I won't get into the approximations, but under certain conditions, you need a more exact form, particularly when beta becomes very small. So the key differences between beta Poisson and exponential, you see the exponential in the red solid curve. Beta Poisson are the other dashed curves on this graph, which are written at different values for alpha. Alpha 1, 0.5, 0.1, 0.02. The x-axis is dose divided by n50, so that all the curves coincide at the median effective dose. As alpha decreases, the curves become more and more shallow. And the most extreme on this is alpha 0.02. There are almost no pathogens that I've seen. We probably examined 30 or 40 of them at this point that have as shallow of an alpha 0.02. I would say 0.1, maybe slightly lower, is the most shallow that we've seen by examining data. Now, one thing I want to point out, and I'll emphasize this in the next slide, is if you look down here, it's tempting to say, well, gee, below a dose of 0.01, I have no probability of adverse effect. But on the next graph, which is the same as this, except I'm going to have the response on a logarithmic axis rather than an arithmetic axis, you see that basically all the curves wind up going down in a linear fashion at low dose. And they never go precisely to zero. By a linear fashion, I mean, if I look at the slope of any of those lines, there's a one-to-one slope on the log-log axis for the beta Poisson and the exponential. We call this low-dose linearity. And the absence of a response precisely at zero means that these are what I would call no threshold models. There is no average dose where you can perfectly be assured that the risk or the probability of adverse response is equal to zero, which is often discomforting to a lot of people because it means if you're asked what the safe dose is, often the lay use of safe means zero risk. And you've got to say, if you rely on that definition, there is no such thing as a safe dose. So we have to start examining what risks are acceptable. Remember, very early on in the course, I gave you a risk paradigm. Determining acceptability is in the realm of risk management, and we need to incorporate other factors, economic, political, and so forth, into the decision-making process. And in fact, we're seeing this playing out right as I speak with the various decisions being made about reopening or partially reopening. Very quick breeze through on this slide for the more mathematically inclined. The beta Poisson and the exponential are really special cases of this broad general framework where we look at three probability distributions that incorporate the variability of organisms in our sample, the proportion of subjects that might require more than a single organism to survive to become infected, and then of the subjects who ingest a certain number of organisms, how are the numbers that survive distributed? They may not be independent and identical. They may have some other distribution. Suffice it to say that there's no circumstance that I've yet encountered, or my students or anybody else, who's looked at microbial dose response modeling that requires anything more complex than the Poisson or the beta Poisson. But the tools are out there to apply. Now, I'll just use one set of examples for this. You know, I've used the term threshold before. Some people would call a threshold model one where you require more than one organism to survive in order to yield an infection. So we can go through the mathematics using the previous messy equation to develop threshold models. And you'll see with the presence of thresholds, whether it's 2, 3, or 5 organisms for K-min, first of all, the dose response curves now become steeper than the exponential. And finally, on a log-log curve, the slope at low dose is steeper than 1-to-1. In fact, the slope is equal to K-min. So if I require 2 organisms, the slope is 2-to-1 on a log-log curve, 3-to-1, 5-to-1, and so forth. Although nowhere, again, is the risk precisely equal to 0. But for this K-min greater than 1 set of models, the risk drops off more steeply at low dose than for exponential. Now, we haven't really incorporated a lot of details about biological and physical mechanisms in here. We haven't accounted for the actual details of multiplication of pathogens in the host. I and my students have done some work on this. This would allow us to more explicitly look at multiple doses and incubation time. And I'll just mention this and say, you know, A, stay tuned. B, I'll be glad to interact with any students if they want to get further into this literature or these issues. So how do we fit dose response models? And I'm not going to give the nitty-gritty detailed statistical methods, but I just want to give you an overview so that you can conceptually understand how we do the fitting. So remember, our design is we have a set of experimental subjects who are divided into some number of groups. In each group, we expose the group to an average dose. Again, Poisson distribution. Of the total number of subjects in a group, a certain number are positive by whatever criteria we want to use, whether it's fever or illness or antibody testing or what have you. So this experiment is quantal, meaning that I'm counting the total number of subjects and total number of positives in integers. I'm assuming a Poisson average dose between subjects, and then I'm assuming that the response of each subject in a dose group is independent and identical to the response probability of the other subjects in the dose group, which leads to binomial variability within the dose group. So we use a technique called likelihood. So if my experiments give me a total number of subjects, TI, and a number of positive subjects, PI, at each group, and I were to expect a positive probability in that group, pi sub I, then this would give me the likelihood of actually observing the results that I obtained. Now, the principle of maximum likelihood is a well-enshrined statistical principle that says, well, if I really don't know what pi sub I is, then my best estimate is obtained by maximizing the value of pi, by finding the value of pi sub I that would maximize this probability. If I have multiple doses, and if I take the logarithm of both sides, I would multiply the f sub p's together. By taking the logarithm of fp, I sum the logarithms of fp. I'll get a lot of constants that will be the various factorials that are independent of anything but my observations and my predicted proportion of positives. So I can ignore those. And then I can ask, well, what is the set of pi sub i's that would maximize that log likelihood? Now, the best possible estimate we could get is when our estimated proportion of positives are equal to the observed proportion of positives. If I have a dose response model that predicts pi is a function of dose, my likelihood can be no better than the perfect fit. You know, think about an ordinary regression problem. The best possible regression you can have is if your regression fits perfectly through all the observed values. But if you force a functional form, let's say a straight line, it can do no better than that in terms of correlation. The same thing here with likelihood. This is just a mathematical simplification. We want to minimize the quantities on the right, which could be from a dose response function, exponential, beta Poisson, or something else. I can do this in a variety of platforms. Excel, although I tend to say never do Excel for serious research. R, MATLAB or Mathematica, Python, etc. So we've done that, and really the objective of what I'm talking about here is not how to fit dose response models, but what to do with them. And so this is for a study that was done some years ago and by Ward, who administered in the course of a vaccine trial rotavirus to human volunteers. And our format here is similar to what I presented with the cryptosporidium data before. Our dose is on the x-axis. Our response is on the y-axis, the left-hand panel being log transformed scale, the right hand being arithmetic scale. I've shown the observed proportion by dots, the exponential by the red solid line, the beta Poisson by the dashed blue line, and I've got two other models by comparison here, the log probit and a theoretical upper limit. Log probit is a purely empirical model without theoretical basis. The observation of fitting this data set is that the beta-Poisson fits better than the others. We regard it as being adequate. The points are close to the blue dashed curve, and the deviations are in line with what we would expect from natural variability, given the fact that we're dealing with a small number of samples of individuals at each dose group. Now, what happens if we have multiple doses? So let's say you're exposed to an average dose of 0.1 viruses today, 0 for the next 5 days, 0.01 on day 6, et cetera, et cetera. How do you determine the overall risk? And the answer is fairly straightforward. For low-dose linear models, as long as the risk is low and the dose is low, and low-dose linear, as I said, applies to both exponential and beta-Poisson, really all you need to do is to add up the doses and apply your dose-response model to the summation of concentrations. If you're at a higher risk and higher dose regime, then you have to start out with this, calculate the risk at each day, and do the extended product. And for more details, here's the reference to that result. Now, there are some interesting questions that really form a lot of what some of my graduate students have been working on. How do we describe multiple dosing and couple it with what happens within the host in vivo? How do we include susceptibility factors, host age, immune status? In the current pandemic, it appears that issues such as obesity, maybe hypertension, and so forth may influence susceptibility. How do we incorporate those? How do we incorporate time to adverse effect? And I'll talk about time to effect in a minute. How do we validate, particularly when we use animal dose response data against human data? Pathogens may be variable. How to account for those? How do we account for data that may be obtained via one route exposure to exposure via another route? And how do we deal with situations where there may be both adverse microbial exposures as well as adverse chemical exposures? As I said, we've done a large number of dose response models. This is a compilation of an inventory of many of them put together with colleagues at Michigan State and Ohio State. But there are other dose response models in the literature that we haven't yet accumulated on this wiki. So let me take a brief break now. And I'll come back and talk about SARS, and then give an example problem.